Hello all, this is Silas Gross with Lab 2 for Physics 2. This is all about charge again. The purpose of Lab 2 is to create a more sophisticated model for finding electrical forces on a clear Scotch tape by considering it as a line of charges, this time instead of a point charge. Key terms, we're going to be using the GLOW-script computational model to show everything, and then we used the electric field, electric force, and gravitational force equations. For the preview, we will find that considering multiple charge points will raise the Q, or the charge, of each point when compared to a single point charge, and we will also find that this will be more accurate. Physics steps. For each point on the top tape, the dE equation was used to calculate the electric field. This is where you use a linear charge density. All we're saying is that we're using this equation, with this lambda being the linear charge density. And all that means is that for each point, we're calculating the forces acting on it by each of the points on the bottom. So for each top point, we're calculating the force of each bottom point acting on it. This assumes that all charge across these points have the same Q, they're all the same, and then the assumption is that there's no air resistances that would act against the force of gravity and against the force electric, and we'd have to find another thing to look for. On the system and surroundings, the system was the high piece of tape, tape B. The surroundings was the Earth, with the gravity acting as an attractive force going down, and the lower piece of tape, tape A, was the had electric force. It was a repulsive force going up. Initial conditions, you can see them all here. They're not very important. The only important one is really the estimated charge, which we found in Lab 1 to be 1.186, yada yada, but this is going to be pretty inaccurate. You can see this here with our calculation of Q. Now stay with me, this one's a little rough. We can see that this top arrow, this little white colored one over here, is way too small. It's not as big as this downward arrow, which represents our gravity. So we know that something is wrong here. So we know that our force of gravity is this equation, this is what we found it to be, and that our force of electric going up has to be equal to the force of gravity for there to be no motion. But right now, our Fe is way too small. So we're going to look at our equations, and we're going to do something different to get a new Q to put in to find a new Fe. So we know our force electric is equal to Q of top times the electric field, and the Q top is going to be equal to the Q bottom, which is going to be equal to the small q. They're all the same. And so when we look at our electric field equation, we see this here, but really we're only focused on this Q right now. We can consider this Q, this K, and this R squared to all be some constants. That's what we're going to set it to. We're going to set it to this hashtag, which is representing some constant. So we can see that our force electric is basically just Q times E, but E is just some constant times Q, so really it's just some constant times Q squared. And so it's just some constant times Q squared. That should be squared there. And so Fe old is just equal to some constant times Q old squared, and Fe new is just some constant times Q new squared. So Fe new is still just equal to force of gravity, which we set up here. So Q new is, Fe new divided by Fe old is going to be equal to some constant times Q new squared times Q old squared, which is just going to be equal to Q new divided by Q old, all of that squared. So then we can rearrange our equation to find Q new equals Q old times square root Fg over Fe old, yada yada. This is what we find. When we plug it in, it works. Great. All that's going through the code is that the outer loop picks a point on the top tape, it's our observation, location for E field, then the inner loop iterates through each of these bottom points and calculates the force acting on it from by combining all the vectors, and the green arrow is just all the sums from those vectors. Similarity and differences. It's fairly similar to the charge found in Lab 1. Obviously it was too small and we had to change it, but it was only a 54% error. So the sources of error that could be found to where this wouldn't match in real life is that the distance between the tape wasn't exact. We found it to be an inch, but there may have been some parallax error and human rounding error. The tapes may not have had the exact same charge, hopefully they did, but handling one more than the other could cause there to be some differences. Air transfers electrons that could change the charge between each point. The tape may have been in motion while we measured, getting us the wrong distance. Now what if questions? The charge that we found by the point charge method was less than the estimated charge for the line charge method. We found that we needed a higher charge for the line charge method. Why? The line charge we did was more accurate. It's not the most accurate. Well, this one was more accurate, actually. This one was the most accurate. But if we did it by only considering 10 points, it'd be less accurate than considering every point. But it sums up the electric field of the smaller segments of the bottom tape on the top tape, whereas the point charge only accounts for one electric field vector, making it less accurate than the line charge, which can do massive amounts of electric field vectors. Basically, we're saying that more is better in this instance, and by adding up all of the charges of one point on another, adding up all of the charges from multiple points on one point, and then doing that and iterating across that gives us a much more accurate force electric. Thank you.